Did you say that?
That's basically what you said.
This is an answer. Yes. And you're doing it through
No air horn? No air horn? Okay.
All right, we are going to get started. All right, thank you everybody for being here today on this special day for Michelle Ntampaka, who is going to be giving her tenure colloquium. So it's a pleasure to introduce Dr. Michelle Ntampaka, an associate astronomer here at Space Telescope Institute, and leading voice of the intersection of cosmology, data science, and machine learning. Michelle is the deputy head of STScI's Data Science Missions Office, where she helps guide our strategy for bringing advanced statistical and computational methods into every stage of astronomical discovery. Michelle's research focuses on some of the most challenging questions in modern cosmology. How we can use galaxy clusters and the large-scale structure of the universe to prove the underlying cosmological model, understand the fundamental physics that shapes cosmic evolution, and understand the fundamental physics that shapes cosmic evolution. A hallmark of her work is the marriage of sophisticated machine learning techniques with physical insight. Rather than treating algorithms as black boxes, she develops interpretable, trustworthy models that allow us to extract real cosmological information from complicated, often imperfect data. Her studies on domain adaptation, simulation, realism, and rigorous model validation are now shaping the community's understanding of how to apply machine learning responsibly in astrophysics. Michelle earned her PhD in physics from Carnegie Mellon University, where she worked on classroom cosmology and dynamics. After completing her PhD, she was a member of the inaugural class of postdoctoral fellows in the Harvard Data Science Initiative, and then she joined the STScI science staff in 2020. She has since then built a diverse portfolio of influential research spanning deep learning for cluster mass estimation, forward modeling, and hybrid approaches to extracting cosmological parameters. Her contributions have been recognized with honors, such as the American Physical Society's Blewett Fellowship. Prior to her research career, Michelle also spent a decade as a classroom teacher, and she has traveled to train secondary science teachers in Rwanda, an experience that continues to inform her commitment to clear, inclusive, and impactful scientific communication. Across all her roles, Michelle exemplifies what it means to combine methodological rigor, physical intuition, and a deep commitment to advancing the way our community uses data. Her work is helping define the future of data-driven cosmology, and it is a privilege to have her as a leader here at STScI. Please join me in welcoming Michelle Ntampaka.
Thank you so much. I am so excited to get to talk to you all this afternoon. I have to admit that I have been looking forward to giving this talk, I think, since I got the phone call offering me the position in 2020. So I am just delighted. We are going to have an interdisciplinary time this afternoon talking about not just astrophysics, but also methodological tools that allow us to interpret our data. And I wanted to start by highlighting that interdisciplinary aspect. I wanted to talk for a minute about how, as a machine learning expert, I think about cosmology, and how, as a cosmologist, I think about machine learning. So as a machine learning expert, I would argue that cosmology is the ideal sandbox for the work that I do. Why do I think that? We have rich current and upcoming survey data. We've been hearing a lot about the community planned surveys for Roman and the calls for new surveys for Roman, and I'm so excited about them as a cosmologist and a machine learning researcher. Astronomers have a culture of sharing our data. So we're not working with medical data where there are HIPAA or privacy concerns. We openly share our data as a culture. We have well-posed questions and data symmetries that we can exploit. And our data are, I'll say it politely, they are non-monetizable, right? The data that we use cannot be used to sell something. Unlike sort of my Amazon shopping habits, Roman data won't be useful for selling things. But the flip side of that is machine learning the right tool for cosmology? So as a cosmologist now, how am I thinking about machine learning? I'm hearing some ringing. Are you all as well? Yeah. Is there something we can do to fix that? Maybe I need to just step back from these a little bit. All right, we'll try again. Okay, so as a cosmologist, I'm now thinking about, is machine learning the right tool for us? And I'd like to make the argument today that machine learning can be extremely powerful, but it doesn't see the way that humans see. Our ability to validate our training simulations is limited, and so we should seek to understand our models and use them as partners in cosmological discovery. So I'm sorry to disappoint. If you came here for the talk that said, machine learning can give us an order of magnitude improvement, and the only thing we have to pay is our physical understanding, if you came here for that talk, you are in the wrong room. There's a lot of nuance that we're going to unpack over the next hour about how to use machine learning as a partner in cosmological discovery. Before we unpack the methods, though, let's talk a little bit about the cosmological object that I study, and that is galaxy clusters. I am interested in using clusters as a cosmological probe. Our modern cosmological model, Lambda CDM, describes the structure of formation in the universe over cosmic time. And this is a quick summary of what our modern cosmological model is, all right? This tells us how the universe spends its energy budget. A really tiny slice of the pie is regular matter. So that is stars and gas and dust and you and me and all of chemistry, right? And all of biology lives inside of that tiny 5% slice. A much larger slice of the pie is dark matter. Dark matter drives structure formation in the universe. And the biggest piece of the universe's energy budget is dark energy, which drives the accelerated expansion of the universe. And my research mostly sits in the dark matter slice of the pie. What I said was, dark matter drives structure formation in the universe, and let's look at what that means. So this is from a simulation. The early universe was very smooth and homogeneous, with tiny overdensities at the quantum level. And tiny overdensities over time accreted and pulled in nearby matter through gravity, resulting in the modern day cosmic web. So you're seeing right now, you're seeing dark matter, but galaxies populate this cosmic web as well. So here's a snapshot of what that looked like through time, early time on the left, late time cosmic web on the right. And that cosmic web is going to host dark matter halos, underdense voids and filaments. If we could look at it in 3 dimensions, you would see sheets in there as well. And in the largest dark matter halos live galaxy clusters. So we're looking now at dark matter halos that are of order 10 to the 14 times the mass of the sun. And inside of those live dozens, maybe hundreds or even of thousands of galaxies, all gravitationally bound. Okay. Here is a composite image of a galaxy cluster. On the top left, you're seeing it in the infrared. So you're seeing there those, possibly thousands of galaxies that are bound inside of that cluster. On the bottom left, you are seeing the hot intercluster medium that glows in the X-ray primarily through thermal bremsstrahlung. So these can be viewed across the electromagnetic spectrum, and I'm interested in them as a probe of our cosmological model. I'm going to show you a very beautiful picture. This one is my favorite galaxy cluster because, of course, we have favorites of the objects that we study. This one is Coma. I love Coma because of its historic significance. So in 1933, the Coma cluster is where Fritz Zwicky famously inferred the existence of dark matter. This is a very beautiful picture of Coma. And may I have your permission to share an ugly picture of Coma as well? Okay, great. So this is an ugly picture of Coma. This is Coma as Fritz Zwicky saw it. 8 galaxies whose line of sight velocities he was able to measure, and one that he wasn't quite sure about, he thought may have been an interloper in the fore or background of that cluster. Okay. So Zwicky looked at these line of sight velocities and also counted up the mass that he could see, and saw that the velocities were too big. Right? The speed of those objects was too large for Coma to be gravitationally bound. And in his 1933 paper, kind of tried to work through why that might be. One of the things he thought might be happening was that perhaps Coma was in the process of blowing apart. But the piece that stuck was this. I'm going to read it to you. In order to obtain the observed value of an average Doppler effect of 1,000 kilometers per second or more, the average density in the Coma system would have to be at least 400 times larger than derived on the grounds of observations from luminous matter. Right? There's matter here that he can't see. That's the only way to explain these velocities. If this would be confirmed, we would get the surprising result that dark matter is present in much greater amounts than luminous matter. And returning to this friend, that is in fact exactly what we see. That our modern cosmological model, structure formation is really driven by this dark matter that seems to be interacting primarily or perhaps even exclusively through gravity. I am particularly interested in clusters as a cosmological probe. And what I'm showing here is, on the y-axis, the abundance of clusters. So the number per unit volume per bin. And on the x-axis, the mass of those clusters. So you can see that the massive clusters are really rare. the low mass clusters much more abundant. And the abundance of clusters is driven by parameters of the underlying cosmological model. I'm highlighting here sigma 8. So in the yellow solid, you're seeing a low sigma 8. The blue dash dotted is a high sigma 8. Sigma 8 is the amplitude of matter fluctuations. Said very simply, it's how clumpy the universe is. It's a measure of the clumpiness of the universe. All right, so cluster abundance is sensitive to that underlying cosmology, but it's hard to disentangle it from cluster mass or from biases in the cluster mass. So I want you to imagine for a second, I want you to take a look at the lime green dashed line, okay? I want you to imagine some uncertainty in cosmology that is shifting that line basically up and down. And compare that to some uncertainty in an underlying mass bias that is shifting that line left and right. Because we're working in a power law regime, a nearly power law regime, right? There's some delicate curve there, but a nearly power law regime, it is really hard to tell apart a change in cosmology from an unknown mass bias. And this is where my research comes in. So I developed the tools that help us to interpret cosmological large-scale structure and disentangle those two uncertainties from one another. The motivation for this work was super crisp up until about 2023. All right, let me tell you what the story was pre-2023-ish. Okay, the story went something like this. Our early time measurements of sigma 8 were large. They predicted many more clusters than we were seeing. So those early time CMB, top right-hand corner. All right. Late time measurements of large-scale structure were in tension with that, sitting kind of low, predicting many fewer, or seeing rather, many fewer clusters. Interestingly, attempts to pull the Hubble tension into agreement makes this one actually worse. So there's not a solution there that pulls both into agreement. All right, that was pre-2023. The E-Rosita result in 2024, I think in a lot of people's minds put that to rest, but there remains a delicate tension there that I think has not still been fully explained. If that tension were due to physics that we haven't yet built into our cosmological model, I, as a physicist, would be very excited about that. And if the tension were due to systematic effects that we have not yet built into our models, I, as a sort of stats nerd, would be very excited about that. So I actually can't lose, regardless of which way this goes. The question really is kind of, how am I going to be excited? I want to take a minute to focus on this particular result. This one is my cosmological constraint, and it has different potential sources of systematic error than all of the other ones. A lot of those places where we blame mass bias as the culprit for this tension really boils down to a lack of understanding or a lack of appropriate modeling in gas physics. The one that I'm going to highlight right here is fluid dynamics, so no gas physics. For this constraint, I analyzed the Hex SZ clusters. Those are Ken Rhines's spectroscopic follow-up of an SZ complete sample of 83 clusters. Pulled from the SDSS DR6 and 10 out to about a redshift of 0.3. And when you plot up the cluster's mass distribution in blue solid compared to mock observations derived from simulations, that's the red with error bars, those don't agree very well. All right, so I'm just telling the same story that I told before using different figures and different pictures, right? We are looking at this, we're seeing this tension again. One solution is to say, we're measuring the blue curve, we're measuring those masses wrong. There must be a mass bias, right? One solution is to say that there's some underlying mass bias that we didn't account for in our mass estimates. That's not the only solution though. The other solution is to blame the physics. So another solution is to assume that the simulation's S8 or the simulation's sigma 8 was wrong. So going back to this original image, I took a look at cluster dynamics to try to understand what in the world was happening here. I developed a test statistic called the velocity distribution function. Here what we are looking at is a forward modeled averaged distribution of, on the y-axis, velocity, number of galaxies, and on the x-axis, velocities in that bin. You can see in the blue the observed clusters, the data. In the red, the fiducial cosmology, that's the high sigma 8, the Planck cosmology, and in the green, the best fit. So to summarize really quickly this piece, we developed a statistical approach to interpret cluster dynamics in the context of cosmology. The constraints favored a low sigma 8, and unlike many other low measurements of sigma 8, my results can't be explained away with gas physics uncertainty, so it must be some other systematic error if it's in there, or it's physics. All right, so to pull back here to the really big idea from this introduction in cluster cosmology, there are tensions in the current model, and trying to understand what has driven those tensions. Is it uncertainties in physics, or is it uncertainties in mass bias, is where my research fits in. Trying to develop data-driven approaches to disentangle these two things from one another. And now I want to pull into this big claim of, or this big discussion of, is machine learning the right tool for cosmology? So let's start with the statement about machine learning can be extremely powerful. For this, I want to highlight some work that I did, rediscovering that cluster cores are messy. For this, I looked at, or I asked, can machine learning outperform traditional methods to estimate galaxy cluster X-ray masses? And if so, how? The first question when tackling a machine learning meets astronomy problem is really like, is this a good problem for machine learning? And the recipe I have, it's very simple, I have written on the right-hand side. If you have a traditional way of tackling something, a scaling relation, say, and then you have evidence that there is some unused signal, something that is not being built into that scaling relation or not being used in that scaling relation, you have a potential problem that would be good for a machine learning solution. In my case, I have a scaling relation between, on the x-axis, cluster mass, and on the y-axis, cluster X-ray luminosity. And morphological signals, so things about the asymmetry and the shape and the clumpiness of those clusters, correlates with whether it sits above or below the best fit line. So that's some indication that machine learning would be a good solution here. I used mock observations of galaxy clusters from the illustrious TNG simulation as they would be seen by the Chandra X-ray Space Telescope. And for this, applied a convolutional neural network. So convolutional neural networks are the bread and butter of machine vision. And the way that they work is sort of in two steps. In the first part, you've got convolutional filters that are sliding over that image to extract features. When I say features here, I mean things like colors and edges and gradients and textures and shapes. All right. Then over on the right-hand side, you've got a fully connected network that takes those features and applies a label at the output. I'm showing a classification here. This is neither a dog nor a cat, it is a bird. Right. But there's no reason why convolutional neural networks have to be used for classification. They can also be used for regression. So you can apply a continuous value label on the right-hand side as well. And these are the results from that effort. In the red band, you see the previous state of the art, and the purple and pink are results from the convolutional neural network, right? Giving on average about a 20% improvement over the state of the art. but I promised you that this talk was not going to be about machine learning gives better results and all you have to do is, give up your physical understanding. So we're not quite done yet. So machine learning can be extremely powerful, but it doesn't see the way that humans see. All right, the next slide that I'm about to show, if you have seen me give a talk before, you know what this next slide is. If you have not seen me give a talk before, you might not know what this next slide is, but I think this might be a room full of experts, so I think we might actually be good. Can anyone tell me what this is?
A horse.
It is a horse, absolutely. How do you know that it's a horse? It looks like a horse. It absolutely does. Can someone unpack that for me a little bit?
It has hooves.
It has hooves. It sure does. 4 of them, as a matter of fact, all in the frame. Yep. You've seen other horses before. How many horses do you think you've seen before? Hundreds. Excellent. Real ones or pictures? Both. Excellent. How does machine learning know that this is a horse? Trained. Yep. It saw a lot of them before. Absolutely. There was a really impactful to me personally and to my research philosophy personally, impactful study that asked this exact question: how do I know that this is a horse? And the team found that for the horse images in their data set, the most important feature was a copyright stamp that was in the bottom left-hand corner of all of their horse images. This is from that paper. Okay, so here we have an image of a horse with the stamp, and next to it, pixel importance. So in red, the most important pixels for classifying that image. When that source tag is present, it is correctly identified as containing a horse. When you remove that stamp, this image is now no longer classified as being a horse. Even more concerning, when you add the stamp to the picture of the car, it is classified with high certainty as containing a horse. Okay, why are we talking about horses in an astronomy talk? We are talking about horses, number one, because this is my favorite story to tell, but number two, because if we're going to trust our data to these tools, we want to understand why they're doing what they're doing, right? We want to be able to know that they're latching onto things that have physical meaning and that they're interpreting our data the way that we want it to interpret. Okay, so going back to labeling these clusters with their masses, we can do a similar thing. We can look at pixel importance. What I'm showing here is as a function of distance from the cluster center on the x-axis, how important are the pixels? And something really kind of cool pops out, and that is that the model has learned to ignore the cluster centers. This is kind of cool for 2 reasons. The first reason is we actually don't simulate cluster cores consistently across simulation code bases. So if you take, initial conditions and you hand those initial conditions off to 8 different teams with their 8 different code bases and ask them to simulate that cluster, you're going to get 8 different answers in the cluster cores. But the outskirts, we simulate really robustly. The second thing that's going on there, and these are tied together, is that there are a lot of astrophysical processes going on in cluster cores that cause those regions to not be as closely tied or as closely influenced by the gravitational well that the cluster is sitting in. So it's really cool that it learned how to ignore cluster cores. This was actually already known in the literature. Adam Mance wrote a paper that basically said, hey folks, let's cut out the cluster cores. If we just look at the outskirts, we get more robust mass measurements. So it's really cool that the machine learning found it on its own. And this was my first hint that machine learning could be used as a partner in discovery, not just as a black box for getting that factor of 10 improvement. But there was one cluster that didn't want to behave. That's this one right here. And we can take a look at that cluster that acted a little differently because it tells us something important. On the left-hand side, a typical cluster as seen in the X-ray. On the bottom, white pixels are important, black pixels are basically ignored. The outlier cluster had these 2 pixels of cold, bright, X-ray bright, infalling gas, non-physical, just some weird simulation artifact that the model incorrectly identified as the cluster core. So this is cool. By interpreting what's going on, we can figure out where we trust and where we do not trust our model. Okay, to summarize here, I applied image recognition, a deep convolutional neural network, to measure cluster masses from X-ray mock observations. The output was a 20% improvement over the state of the art. The interpretation is in line with other literature that the model learned to excise the cores. Okay. ML is extremely powerful. It doesn't see the way that humans see, and our ability to validate our training simulations is limited. I've got another activity for us here. I'm going to show some data. They're XY scatter data. I'm going to give you the mean and the standard deviation in X and Y, as well as the correlation, and I want you all to find the outlier for me. Okay. Someone say the obvious thing out loud. They are all the same. Great. Okay, let's go ahead and visualize this and see if they are, in fact, all the same. Okay. This is the data source dozen. They are 13 XY scatter data sets engineered to have the same mean and standard deviation and correlation. Oops. Let's go through those one more time. No. There we go. Okay, now that you visualize them, does anyone have a favorite outlier? I like the dinosaur as well. I'd be willing to hear arguments against the dinosaur, but I like the dinosaur as well. All right, we can tune our simulations to match simple summary statistics of observations, but even with those simple tests, we still might not capture important patterns or correlations in our physical models, right? Machine learning is very flexible. And if we apply these tools and it picks up on sort of the dinosaur-ness of the data set, and all we're tuning to is mean and standard deviation, we're going to get ourselves into a lot of trouble. And deep learning acts in unexpected ways. So this paper from 2022 looked at ImageNet trained convolutional neural networks and found that they were much better at textures than at shapes. All right, on the left, the texture of an Indian elephant, correctly identified by machine learning, probably a little bit harder for a human. The center is a cat. Everyone agrees. Everyone is very good at identifying cats, machine learning and human alike. What's interesting they found, though, is that if you have a texture-shape-cue conflict, the human is going to tend to identify the cat in that image, and the machine learning is going to tend to identify the elephant texture in that image. Okay, we've got horses, we've got dinosaurs, we've got cats, we've got elephants. Very strange astronomy colloquium here this week. But the point is that the power spectrum that cosmologists use all the time, it is such a useful compression of cosmological data, but it is not complete. Right? In the 2 images that you see on the right there, Cole's 2005, those on the left, this one right here, an n-body simulation. On the right, another simulation. They have the same power spectrum, but completely different phases, right? So the power spectrum is not a full representation of that data. All right. Machine learning, powerful, doesn't see the way that we expect it to. We're limited in the way that we interpret our training simulations. We should seek to understand our models, not use them as black boxes, but rather try to understand them. I want to highlight some work on interpreting X-ray survey data that I led. Here I'm asking, can machine learning interpret X-ray survey data? Can carefully engineering a deep learning model lead to trust in the model's output? All right. The core piece of machine learning that I want to build from here is an autoencoder. These are really neat. They are a type of unsupervised learning, meaning you don't have to have labeled data. You're going to put in a signal on the left-hand side. It is going to summarize that signal in the center and then try to recreate that signal. So you've basically got some input signal. This and the one on the right-hand side are exactly the same. An encoder, a terse or latent space, and then a decoder. It's kind of like a flexible version of principal component analysis. I'm going to abstract away all of those because this is going to get very messy very quickly. So this is the exact same thing as you saw before, just abstracted away the fully connected network. And for this, I built a supervised encoder that looks something like this. The architecture follows what an astronomer would do. So what I've got here is a list of cluster parameters, right? So each of those rows is a different cluster that I've summarized according to their observations. We are going to summarize that cluster in the only parameter that tends to matter for cosmologists. Here in this terse space, we are going to build something like a mass proxy, or at least we hope that's what we're going to build. Then allow that model to see all of those cluster mass estimates to infer the underlying cosmological model. So it follows what an astronomer would do. There's a physically motivating reason behind this, and that is that getting the maximum amount of information per object sort of as a first step is generally an approach that's going to give you more robust results, especially when you've got a diverse population. So we're attacking this just the way a human would. This is about to be the most boring slide of my presentation, so prepare yourself. The results are at about the expected theoretical limit. That is not exciting at all. All right, what I'm showing here is the estimates of sigma 8, true and predicted. And those error bars that you see, or the distribution there, is about what you'd expect given the cluster population size that I gave it. I woke up one morning to the results on the right. Okay, recall that the ones on the left are at about the expected theoretical limit. The ones on the right, there are error bars. They are hiding behind those points. They're a factor of 10 improvement over what should be the theoretical limit. So because I've carefully engineered this model, I can start to poke at this and try to understand what in the world is going on. Have I made a great discovery? At this point in time, I had enough expertise with deep learning to know that no, I had not. I had messed up, right? And let's find out why. So to understand what's happening, we can visualize how that terse value, the one in the middle, correlates with mass. 2D histogram. And in the case of our trustworthy results, that terse value tightly correlates with mass. It's doing exactly what I hoped it would do. It is building a mass proxy. The suspicious results really have me concerned because this model should be building a mass proxy and it's not doing anything like that. Those are totally uncorrelated. So this is really worrisome. Okay, even worse. Now I'm looking at the terse layer value and the underlying cosmology. This looks exactly the way I'd expect it to look. From a single cluster, we should not be able to figure out the underlying cosmology. In the suspicious results, tightly correlated, very worrisome. And that's where I was able to find the problem. What had happened? The model picked up on a cosmology-dependent simulation artifact. It was the astronomy equivalent to looking for that stamp in the bottom left-hand corner to identify that the picture was of a horse, right? It had cheated. It was able to infer sigma 8 from just one cluster. And I knew at that moment that this factor of 10 improvement was not going to generalize. I could not hand it real data and ask it to infer the underlying cosmology because it had simply straight up cheated. Right, so these results are not robust. The model won't generalize to real observations because it depends on a simulation artifact. So building these kinds of checks into our machine learning models are absolutely essential for building models that are trustworthy, that we can hand our real data to and get meaningful answers out. To summarize this one, we applied a deep learning convolutional neural network that was carefully engineered to mimic a human approach to cluster cosmology. The output predictions were about at the expected theoretical limit, but the interpretation allowed us to build trust that the model was learning as expected. All right. The last line of this that I want to highlight is that we can use machine learning as partners in cosmological discovery. Philosophically, I've come to a place where I see machine learning and deep learning especially as a sort of very creative and very shy lab assistant. It is able to tease out trends in my data that I might not have been able to find by myself, but is very reticent to tell me what those trends are. And that's where a lot of the work comes in. So for this, I want to highlight some work that I did with John Soltis, who was previously a PhD student at Johns Hopkins and has recently joined us as a Lasker Fellow, asking, can machine learning do something that humans cannot? Can it estimate cluster mass accretion rates for individual clusters from multi-wavelength observations? And if so, where is the information? Okay. Up until now, we have been treating clusters as if their only cosmological information is in their mass. All right. Clusters are often treated as self-similar, with the mass being the main parameter of interest, but their assembly history is actually I think the most important and most significant perturbation to that claim. Cluster mass accretion rate can be parameterized as something very simple, just the change in mass over the change in time. That mass accretion rate is a function of the formation history of the cluster. The recipe of mass accretion rates that you get in a volume is a function of the underlying cosmological model. And clusters could be relaxed with a small mass accretion rate. Really, they've just been sort of slowly accreting matter through the filaments that feed them. Or they can be disturbed, meaning that there had been a recent large merger that cluster experienced with a large mass accretion rate. And traditional options for estimating that from a single cluster is significantly limited. We worked with multi-wavelength cluster mocks, so 3 in the X-ray and 1 in the SC. And this, I think, is actually, I showed you my least favorite slide. I think this one might be my favorite slide in the talk. On the x-axis, true. On the y-axis, predicted mass accretion rates for our cluster sample. On the left-hand side, the leading analytical theory. Not a straw man. There simply do not exist good ways to estimate mass accretion rate from observations. The sharp floor that you're seeing there is a result of this model basically takes mass and maps it directly to mass accretion rate, not really pulling any individual details or cluster personality into account. So the sharp floor that you're seeing there is just a result of our selection function for our sample. And the right-hand side, the machine learning model, large error bars, but clearly picking up on sort of the large-scale trends of mass accretion rate in those clusters. We're never done with this slide where we show the results, right? There's always the question of what's going on underneath the hood. How do we understand this? And for this, John led a really cool exploration of how to explore this by dividing clusters into their constituent components. So we took the mock observations and divided them into a symmetric and an asymmetric component. So if you pasted those back together, you'd get the real mock observation. And then made some Franken clusters. So on the left-hand side, high mass accretion rate mock observation. On the right-hand side, low mass accretion rate. I marked those with a star and a hexagon just so you can track them in the next couple of slides. And I'm going to build these Franken clusters that had never been seen before, right? So by mixing and matching and painting the asymmetry on top of the symmetric component. And now we can ask, where is the information? The left-hand side, true. an estimated mass accretion rate. You've seen this figure before. This is just for the regular images. The right-hand side, this was a mix and match with close pairs. The mix and match, they were the same mass, they were the same mass accretion rate. Okay, there's not much of a difference, and so this is kind of cool. There's three possible explanations for why there's not much of a difference there. Explanation number one, all the information is in the asymmetric component. Explanation number two, all information is in the symmetric component. And the last option is that the information is in both, but in a way that's uncorrelated, right? In a way that we can add them both together. We can mix and match. And that last one was the surprising result. Here we're seeing, now these Franken clusters are being made with mismatches in mass accretion rate. And you see the error bars just blow up, meaning you need both the symmetric and the asymmetric component to be able to get a good estimate. But it doesn't matter if they're from the same cluster or not. All right, so here, we applied a normalizing flows model to estimate cluster mass accretion rate. The output predictions were a factor of 2 better than the current state of the art, and the interpretation tells us where the information lies. It is in both the smooth accretion that's happening over filaments, and also in that disrupting accretion that is happening through major mergers. All right, returning here just to ground us before we talk about next steps. All of these pieces of the puzzle really are going toward addressing this question of how can we disentangle mass bias from changes in cosmology as we try to interpret galaxy clusters in the cosmological context. All right, so what are the challenges and what's next? I want to read to you a quote from the 2020 decadal. We are now halfway through the decade. And I want to read to you the decadal's finding on machine learning, and then let's assess that together here at sort of the 5-year mark. So, machine learning has already shown significant success at providing tools for identifying anomalies in data, and it can speed up parameter estimation in large data sets by significant factors. These techniques could lead to transformative discoveries from the new data sets available in the 2020s. Transformative discoveries. I love that part. Could lead to transformative discoveries. I think one place where we really need to address, or you know, the place where we could lose this all is in our ability to address a thing called domain shift. Domain shift is what happens when the simulation does not match reality, when there are systematic differences between the data that you're training on and the data that you're testing on. And domain adaptation is the approach or the handful of tools to be able to manage that shift. All right. Techniques that are available and on the table for us. Astronomers really love calibration, so calibration is always an option that is on the table for us. Machine learning researchers are developing specialized tools that can address that domain shift and be able to manage training on one data set and testing on another. They tend to be stronger for classification than they are for regression approaches. All right. Statistical approaches for quantifying how similar and different two data sets are from each other so that we can know that we're in this domain shift regime that we need to proceed with some care. And I think that there are some astronomy specific techniques to be built out as well. Thinking about how we can do science within the limitations of domain shift, and how we can work from the things that machine learning would naturally produce for us, like a rank ordered list, even if we don't trust the underlying calibration. And so these are the challenges that I'm thinking about over the next 5 years, especially as we're looking into kind of the 2030 decadal. This is the big thing that I think that we as a community, and I in particular, am interested in addressing and building out astronomy-specific tools so that we can manage them. And with that, I will put up my final slide with my claim on the left, a couple of the citations on the right, and I'd be delighted to take any questions.
Thank you very much for this wonderful, very interesting talk. Questions for Michelle?
Thanks for this wonderful talk. Thanks for this wonderful talk. I'm curious, you know, the story you told here of how you have to check with the interpretability of everything essentially and like try to figure out maybe what works, or not what works, but what it sees, is like very relevant now. But do you think in 5 or 10 years we'll be much more able to do what maybe promised 5, 10 years ago, just throw the black box at it and not worry about this? Or will we just always have to do that and it's just part of doing machine learning? There's no way to get around it.
Eric, I've got 2 answers for you. Should I repeat the question for the folks online? Okay, so the question is, will we always have to interpret our models and understand what they're doing? And my 2 answers for you are yes and no. The no is, sometimes there are places where we can accept machine learning as a black box, and that's fine, right? If you're going to use it as a black box, do it on purpose. The yes is, I think, for all places where we are doing science, we want to make sure that we're interpreting our model. Yeah, but there are simply times when they can speed things up, right? I'm thinking about sort of adaptive optics. Like, do I need to understand how or why ML is solving, you know, matrix multiplication or matrix solutions for adaptive? I don't. I can just accept it. Yeah.
Yeah, great talk, Michelle.
Thanks.
So you began with the sigma 8 tension, or SAE, whatever you want to call it. You then showed us all these, you know, these tools that you really innovated on, the improved mass estimates, and maybe even a new way to latch on to cosmological parameters through the mass accretion rate. So it's kind of expected. That last slide with your 2025 estimate of SAE, and I didn't see it. So I'm just, what is holding you back? Is it the lack of the right kind of data? Are you planning to do that in the future?
Yeah. So the question of mass accretion rate as a cosmological probe, I think, is still in its infancy. So our group is exploring both how do you measure mass accretion rate and also how can you use it as a cosmological probe, and can those pieces come together to provide a new estimate. That is still in its infancy, and so it is simply too early for me to be able to answer that question. One of the main barriers is domain shift, is understanding how the simulations that you have trained on and the real data that you're applying the model to, how they might differ, and carefully addressing those differences. So we're finding that that is a real challenge. Yeah. I'm sorry that we're getting the ringing. Do I need to just simply stand farther from you?
This way.
Okay.
Yeah. I'm not here. Yeah.
Okay.
Okay. You have a microphone?
People can hear you.
So usually in astronomy, we use the velocities, the motions of test particles, and the way they respond to the gravitational attraction of a body. That's proportional to the mass, or a deflection angle, something like that. Now, I didn't hear you mention anything to do with the motions of galaxies and clusters, or the effects of deflection of, you know, background images and that sort of thing. What am I missing here? I mean, that's what you need to measure the mass of something. You need some motion of something, or of a photon, or a star, or a galaxy, or something like that. Are you trying to measure masses without using information like that?
So this is a great question. So this early conversation about Zwicky was really focused on velocities and connecting kinetic energy to gravitational potential energy through the virial theorem and using that to infer the underlying mass. The second piece of the puzzle, though, was X-ray. And here, the potential well shows up in X-ray luminosity and temperature.
Are you using temperatures?
Yes,
Okay,
exactly.
well, then I got it.
Yeah.
So it's the velocities of the atoms and the
Exactly.
gas and the potential.
Exactly. Exactly.
Yeah, along those lines too, excellent talk. You were showing a lot of the X-ray data and how that's going to help constrain cosmology. What about with Roman and the weak lensing and maybe also identifying more cluster members at the large radius? Can you apply machine learning to all that?
Yeah, so weak lensing is not my area of expertise, so I'm not going to try to dip my toes into that right here on the fly. One place that I am really excited about Roman data is probing cluster outskirts and the environment in which a cluster lives as a way to start to understand its formation history and try to look back in time through those sort of really wide area surveys around them. Did that answer your question?
Yeah.
Okay, all right.
So, Michelle, you gave us one really interesting equation, which is that a scaling relation plus unused signal is a potential ML solution.
Yep.
I might want to apply that in my own work. So what I would like to know is, did you have a hunch, or do you need a hunch, that there's unused signal there on the basis of some other piece of information? You look at the scaling relation and say, there must be something other than stochastic behavior or whatever. Or is that something that ML tells you?
I think this is actually a question of risk taking in planning a project. So for this particular problem, the paper that I was looking at was Marone 2012 that identified that the morphological, like the shape of the cluster, gave some indication as to whether it was sitting above or below. That said, this was one of the earliest convolutional neural network papers in astronomy. And so I was not in a super risk-taking mood when I was building that one out, right? The ML will be able to pick up on those signals even if you don't have a hunch as to what they are. And at this point in time, there are enough tools on the market that it's pretty straightforward to build out these deep learning tools to tackle it in sort of an exploratory way.
Hi, Michelle. This was great. I'm even more excited about machine learning now after hearing this. I have a more open question from an exoplanet.
Sure.
You showed us two very important. You taught us two very important lessons with this talk. One was summary statistics are dangerous, or they might not capture all your information. Not dangerous. I was too dramatic. The second one on your last paper that you showed was really cool, which was, it's like these different shapes that you can extract from it can tell you a lot of information. So you've been showing us the historic sigma 8s, the M500s, and those are summary statistics on themselves. Can you elaborate a little bit on whether machine learning can find new statistics on observations through studying either simulations or observations themselves? Do you see any future in doing something like that to explore, all the questions that are doing even better?
I think I understand your question, but I think I'd like you to ask it one more time using different words. I'm sorry.
Fair enough. So from an explanation, when I learn about sigma 8 and M500, it's a bit of a historical perspective, right? It's just easier to measure. But now we have a lot of more data. And with Roman, we'll have more, and we'll keep having more data. And I keep wondering if those are the right summary statistics based on your own point. To study the universe as we've been studying it, especially now that we're starting to see tensions and whether that tension can be stronger in different summary statistics than the ones that we're usually studying.
Yeah, so this is, I think, a philosophical question about sort of the interplay between the user of the machine learning tool and the way that the ML finds signals underlying. There are no really obvious, straightforward ways to have machine learning just kind of take your images and hand you the most important summary statistics. That's where the fun is, and that's where the work is, unfortunately. And I think that it really kind of comes down to, let's see if I can find the figure real fast. It really comes down to this, right? Trying to understand what, building techniques that probe what's important and then trying to build the summaries from there. Yeah. So the short answer to your question is, I think this is job security, right? It's the fun stuff, it's the cool stuff, and there's not a really obvious way to automate it.
Marsha.
Michelle, thanks for a great talk. I really appreciate the focus on physical interpretability. I'm also curious, on the other hand, about just the tools and the computing that you're using to do this. And so I'd like to hear a bit more about, the machine learning frameworks you're using. Are you running, what's the scale of computation? And also in particular, there's a bunch of like hyperparameters, choice of networks, and how many layers in your CNN. How do you approach those sorts of things when building one of these tools?
Yeah. The work that I do tends to be small data, surprisingly. None of the stuff that I've shown here has been really large quantities of data that I've had to wrestle with, how am I going to store and move it around? So I tend to work in the small data regime. I tend to work in the engineering deep learning techniques regime. So I will typically rely on libraries like Keras or TensorFlow to be able to build those tools. From there, it is more art than science, which makes it super fun. But I spend a lot of time thinking about things like the perceptive field of a convolutional neural network. How much can it see at one time? And are the physically meaningful parameters of this object contained within that field? And so then you can engineer your model so it sees the right size, right? If you think it should pick up on small or larger scales. So unfortunately, it's a lot of failing and practice and intuition, but it's fun. Yeah.
We have time for maybe one quick question, very last question. If anybody still, okay, go ahead, Alex.
For estimating mass accretion rates, what prevents you from directly comparing the simulations that produce the MOG data to the data to estimate mass rate? Is it just computationally prohibitive, or can you do like Monte Carlo or nested sampling, that type of model?
So what prevents us from just applying this technique directly to observations? Is that the question?
My question is, so I'm assuming that you have some simulated model of the galaxies that are, taking as inputs some parameters that you're saying that you're setting them as the truth, like the mass accretion rate, and then they give you some output, which you're using to do the learning on, and taking that learned relationship and applying it elsewhere. Maybe that's wrong.
So the learned relationship at this stage is not actually an analytical model. It is the machine learning model that has been trained. So applying those to real data would mean taking that real data, putting it as the input, and then getting the mass accretion rate as the output. And one of the biggest barriers for this right now is understanding and quantifying domain shift. So being able to understand and being able to write down how the simulations that we build, which are correct in broad brushstrokes, but may have nuanced differences with real observations, understanding those systematic differences between them. Yeah.
All right, unfortunately, we're out of time, but Michelle is all the time around if you have more questions. And yeah, thank you, Michelle, for this wonderful talk.